Oh, you up and running? So we're looking at problems, we're gonna look at problems 22 to 32 on the sheet that you will be using on day one back from break. And the first problem that we're doing right now is solving the equation, the square root of x plus 3 equals x minus 3. And I'm gonna have you do two things with those problems. One, approximate your answers before you find them. We're gonna approximate. How are we gonna do that? We're gonna do that graphically. And we have been looking at graphs like y, let's say our first graph, square root of x plus 3. And our second graph here, the one on the right, linear function x minus 3. We're going to put them on top of each other. Because that's what you're doing when you're solving equations, is you're really looking at snapshots of where graphs intersect. Sometimes they intersect more than once. Sometimes they don't intersect at all. So we'll get a little look-see here. We'll do it off to the side. There's the xy axis. Let's go -3, gets us 0. So now I've estimated that distance to be 3 units. X minus 3, 0 gets you -3. So that looks to be about the same size. We know that's going up 1 to 1. We know the shape of the square root function looks like that. And so if that's 3 units, let's do 3 of those. 1, 2, 3. I know the square root of 9, but I've got to go out another 3 to get to 12. No, I wanted 6, right? 6 units to get that. 6 units. Oh, God. Let's just estimate. So that's 3. What is that going to be? It's 3 units, 5 or 6, something like that. So just a real rough estimate. Okay. And now let's solve. So we got to get our x's together, and therefore we've got to get them out of the square root symbol. So we'll square both sides. Hopefully that makes sense. We've been squaring binomials for the last 4 months. X squared minus 6x plus 9, that should be automatic. Perfunctory. All right, now we're going to set it to 0, set quadratics to 0, x squared minus 7x minus plus 6. Oh, that's nice. Got to come over here a little bit further. So we got ourselves an x minus 6 and an x plus 1. X minus 1, excuse me. Okay, and that minus 1 is really in that vicinity if we had the bottom half of that inverse parabola. That is really what this is mimicking. All right, so looks like our answer was 6. Not 1. 1 does not intersect at x equals 1. What happens at 1? You get -2 on this side, you get +2 on that side. So you've got to check your answers one way or the other, plugging your numbers in to see if they work. They intersect at 6, 3 as a coordinate, but we're only solving for the x value. All right, and what happened? Why did we get an extra answer? Well, it's what's called extraneous solutions. Got to get fancy in math, right? Extraneous. Think of it just as an extra answer. So here's an equation, x equals 5. There's one answer to that equation. But if I square both sides and then I solve for x, I get 2 answers. But one of them doesn't work. So got to be careful when you square. You might bring in an extraneous root. All right, we're going to be talking about that for the next 2 months. So I'm sure if I missed anything or didn't say anything that I wanted to say, the next 2 months we'll hit it. All right, these problems, after you do them a while, x squared minus 10x plus 34 equals 0, you can do them without any work. That is, if you look at the answer in the original question, which you should do with most every problem that you're dealing with this term, you might find some shortcuts. But let's not take any right now. I've already done a skill worksheet on this, or a video. So it's one of those skill videos, probably in the quadratic section, trying to get some organization of the videos by algorithms now. Let's see how that works. Square both sides, because we're trying to find ax squared plus bx plus c equals 0. And these are the answers. I should have said that in case you hadn't seen that other video. That's what we're after. So binomial squaring, x squared minus 10x plus 25. It's worth looking at the pattern. Save yourself having to do this every time. All right, equals square that, 9i squared. And so that's x squared minus 10x. That's minus 9. Bring it to the other side, it's positive 9. Okay, and so that was our answer. And on the midterm test, you were using completing the square to get those answers. So even off the sides of the square and bring it back to the same algorithm. That's positive 9 becomes negative 9 on this side. Squaring becomes plus minus square rooting negative 9, which becomes plus minus 3i. And then you bring the minus 5 over positive 5. And you can see where we start. And again, we're going to do those for a couple of months. Got every faith in you that you'll get those right. So x minus 3 is a factor if x minus 3 is a root. Or x plus 3 is a factor. And this is one of the reasons we've been practicing this skill. Products equaling 0, very important in math. So there should be no remainder. If this is true, there's not going to be a remainder here. So we got x squared, that takes care of that. 3 times x squared, oh, took care of both of them. So the next thing we want is minus 6x. Let's put a minus 6 there. There's the minus 6x. Whoa, boy, that was simple and easy. So one of the roots is minus 3, and the other roots are plus minus the square root of 6. So we got some knowledge of our roots. Let's get a better look at this calculation. Let's do some putting it in graphic form, finding out some things. And you can do all of this work based on completing the square by averaging the roots. So what is the average of the roots? Minus 3 plus the square root of 6 minus the square root of 6. Those were your 3 roots. And if we divide that by 3, we can see those cancel. Negative 1. Ah, so we could make a new cubic. And we would have an x minus 1, x minus 1, oops, x minus 1, x minus 1. All those 3 dimensions, we could complete the cube and put this in graphic form. We'll put it in graphic form in a moment. But what's the quick way? We don't need to find the roots. We can simply do minus b over 3a. And we're going to get negative 1, I believe. So where am I? Oh, minus b. Negative 3 divided by 3 times 1. The a term is 1. It's not written. Oh, there's negative 1. Oh, okay. So let's put that here. Let's put this as negative 1. And let's find out the rate at which that's going down. And you can use algebra, but you're going to be doing it with calculus. But you can do it algebraically. And it turns out it's c minus 3ah squared. I'm going to call that m, the multiplier. And c in this case is minus 6. Minus 3a is 1. That's the coefficient of x cubed. And negative 1 squared gives me 1. So it's negative 9. So I'm going down at 9 to 1 at this instant. Going down at 9 to 1, right there. Down 9 to 1 at that instant. Which means in calculus, you're going to do the tangent line. And to find the tangent line, we need the coordinate. We didn't find the coordinate yet. So we got to plug negative 1 in and then do some quick math here. So negative 1 cubed is negative 1 plus 3. And oh, there's that 3 to 1 ratio. Yeah. And they're opposites. That happens in cubics. Plus minus 1 plus 6 minus 18. And so I've got minus 9 minus 10. So this is minus 10. So in calculus, you're going to write the equation of the tangent to the point of inflection, which in this case would be minus 9 times x plus 1 minus 10. And what you're going to find if you want the graphic form is the a term, x plus 1 cubed. If we multiply this out, we're going to get that. Oh, amazing, amazing, amazing. So the rate at which the y-intercept. So what's the y-intercept? Well, the y-intercept is negative 18. And the rate at that instant is negative 6. We've looked at that in other videos. So I'm going down at 6 to 1. Why don't I do that? A little less steep. At 0, negative 18. This is always the rate for polynomials, the linear term. And so what have I got? I know end behavior. This thing is eventually going to, you put 1 million in here in cubic, whoo, you're going up. So what's it look like? Down here, up, down, down, and up. Okay, and so now we can find these very easily with a formula, which is local max and min is x equals h plus or minus the square root of minus m over 3a. I wish I had all those Maple documents that I did in the 90s, because honestly, I don't remember how I got there. I know what it is from a calculus standpoint, but I did all this really before I knew much about calculus. So, so what is minus a minus 9? Minus 9, right? Well, that's positive 9. And 3 times 1 is 3. 3 goes into 9 3 times, and h is -1. -1 plus or minus the square root of 3. And I've asked you to memorize the square root of 3. So one of our answers is -1 plus 1.73. And the other is -1 minus 1.73. That's very helpful, because that makes this negative 2.73-ish. Right? And we know that 3 gets us a root, -3. So that's got to be really close, because this is below, right? This is quite a distance below our roots right here, right? And then that's got to be -√6. And this has got to be +√6 out here. I don't know what those numbers are decimal. I could find them. √6 is √2 times √3, which is 1.41 times 1.73. So we could get some good accuracy here without a calculator, which is kind of nice. So there's our, it's got local maxes and mins. So this one's got to be, oh, I can figure it out here, right? So -3, -2.73, and -1. So it's got to be, that was the √3. So this one's got to be 0.73 for the local min, right? And I'm not sure what those y values are, right? We'd have to do a little math there. Okay, did I miss anything? I don't think so. Now, for the calculus folks, I'll just show you that you can get to here. Let's do y prime. There's your 3x squared plus 6x minus 6. Y double prime, 6x plus 6 equals 0 when x is -1. Okay, and if you put -1 in here, you get 3 minus 6 minus 6. Well, there's your -9. Okay, so that's your rate of change at the point of inflection. And if you put -1 in here, you get -10. So you put -1, -9, -10 together, and I hope you can see that part of the graphing. And if this end behavior is up and at the point of inflection you're going down, then local maxes and mins exist. All right, that's a mouthful. That's an awful lot, and I'm not even sure I have this centered well enough for you. Oh, terrible. Got caught talking. But anyway, we're going to do it for 2 months. And the videos that are helpful, putting cubics in graphing form. Cubics in graphing form. I'll just put G up there. Explains all of this in more detail, and it's based on completing the cube. And I did that geometrically in a couple of different videos. So if you want to see what it's based on, you're going to have to look there, because I don't think it's anywhere else on the internet. Maybe it is. I mean, certainly writing it in graphing form, I would hope would be there, but I'm not sure. I haven't seen it. All right. 2 sine x plus 7, we're going to graph. All right, sine function in the unit circle is the altitudes. All right, so what happens in the circle? You start walking around the circumference and you start drawing triangles. And if I drew a triangle over there, it's got a certain height. And if I drew the triangle further up, a little bigger angle, bigger height, and the biggest height is at 90, and then it comes, those altitudes come back down to 0. So we start in the middle. Our heights are in the middle. We go up to a height of 1. We go down to -1. And they come back to 0. 0 degrees, 0 radians. 0 radians gets you 0. 2 pi gets you back to 0. -1 occurs at 3 pi over 2. We've got to know the period here. We've got to know a couple of values. Pi gets us back to 0. And pi over 2, 90 degrees, gets us 1. We've got to know these values. Otherwise, you got no prayer graphing. Okay? So when we graph a sine function, this is one period. Doesn't have to be. We could have done one period from here to here. Okay? But most textbooks, most standardized tests and everything are going to be giving you something that looks like this. So how do we go about graphing that? Well, the most important thing is knowing that we want to put a 0 and a 2 pi. We want whatever, however complicated our argument is, we want it to start by making the parentheses 0, and we'll finish one period when the parentheses is 2 pi. And there's all kinds of shortcuts we'll see in the next couple of months. But right now, it doesn't hurt. Draw some horizontal lines dotted like that and put the period in. And then look at the range. Midline is 7. We go up to 9, we go down to 5. What makes this parentheses 0, 0? Well, we put 0 in, the sign of 0 is the height at that location on the unit circle, which is 0. But in this case, it's 7. Okay, because 2 times 0 plus 7 gets me a height of 7. And then we come back to 7 when we put 2 pi in. 2 pi brings me back to the midline. And once you have those two values, you got pi here, you got what? Pi over 2, so on and so forth. But we're going to make these more complicated, but let's start here. All right, so what do we have for the cosine curve? Well, the cosine curve measures the widths of the triangle. So where's our maximum width? Over here at 0. So the cosine of 0 is 1. These functions never get bigger or smaller than 1 or -1. So I'm starting at a max. 0 gets me 1 in this case, and 1 period brings me back to the max. And what's 1 period? Again, 2 pi. So they're very similar functions, right? In this case, pi gets me -1. Where's pi over here? Cosine measures width. Well, that's a -1 for a width, right? We're going to get a coordinate system inside here. And so that's 1 period of the cosine function. And as we go through the next 2 months, we're going to make these more complicated, but they don't have to be. You always want the parentheses, the argument to equal 0, and the argument to equal 2 pi. And there are shortcuts. And we'll look at it. But that's getting the conversation started. Couple more problems. Let's see if this is true or false. This will be rule number 2 of our rules of logarithms. So, is it true that a division of the parentheses gives us a single log? Let's find out. So ln is E notation, right? So you got to know these. This stage, e to the 0.7. If you're in the classroom, then you've got to know those by now. If not, time to wake up a little. So 8 is 2 cubed. We know that e to the 0.7 is the approximation for the number 2 we're using. And I'm raising it to the 3rd power, which means it's e to the 2.1. That's approximately 8. 4 minus 2 squared minus e to the 0.7 squared is 1.4. So e to the 1.4. Oops, I'm getting a call. I'll have to call that back in a little while because I'm not going to make this video again. Okay, e to the 2.1 minus e to the 1.4. But I'm only looking at the exponents. Okay, is that equal to e to the 0.7? 2.1 minus 1.4 does equal 0.7. Appears to be true. So it looks like the rule then is the ln of A minus the ln of B can be written as a single log as the ln of A over B. We'll be talking about that for the next 2 months. So if subtraction is division, then maybe intuitively, we've already looked at the first rule, but I've shown it here log base 5, can you see it? I centered this, log base 5 to 25. I hope you can see we got a 1 plus a 2 here, which is a 3. 5 with the 3 is 125. So I hope just looking at that, you can trust that I can write this as a single log by multiplying the parentheses, which is x squared minus 2x equals 3. First half, we've been studying how to solve logarithms. You put it in an exponential form. X squared minus 2x equals 2 to the 3. So that's x squared minus 2x minus 8 equals 0. So that's x minus 6 times x, what did I say? X minus 4, excuse me, times x plus 2 equals 0. We cannot use -2. We've been starting to talk about the domain of logarithms has to be positives. So let's see if 4 works. Put a 4 in. Put a 4 in. 4 minus 2 is 2. What's the exponent you put on top of a 2 to get a 4? Well, that's a 2. That's a 2. What do you put on top of a 2 to get a 2? That's a 1. And it sure does look like 2 plus 1 equals 3. So there was one answer, and it was x equals 4. Okay, and you don't have to do a ton of those right now. We're going to do one every day till the end of the term. I am doing this because there's some real gaps in Algebra 1. Didn't do enough of these. So we're going to do one every day. I'm going to sneak one in somewhere in the worksheet every day. You set quadratics to 0. I'm tempted to do it by completing the square. It might even be quicker. But standardized tests, you got to get good at writing products, set them to 0. So in this case, I hope you can see x minus 9 times x plus 5. Yep, that's right, equals 0. Sometimes you forget to say equals 0. Leave it like that. That's too bad. So we got two answers, 9 and -5. Okay. And so we're doing some problems repetitively here that we did at the beginning of the term because they're so important. You got to be able to graph. You got to be able to graph y equals 2x minus 7. And if you're not sure, put in some numbers and just plot them. 0, -7. 1, -5. 2, -3. 3, -1. Connect them. You can do that with any graph, right? Just get some table values to see a pattern. Hopefully you don't have to do the table value. Hopefully you know that the y-intercept is -7, 0, -7. Then you're going up 2 to 1 ratio. Okay? You're going up in a 2 to 1 ratio, and it's the same line. And I'm hoping that you can recognize a positive quadratic, right? As a cup shape up. We can see the roots by when this thing equals 0 at 5, and at -7. And our x value of the vertex is in between, so -7 plus 5 divided by 2 gets us -1. And when you plug it in, we're probably going to get a positive, negative, they're going to be the same magnitude. 2, let's see, -2 minus, oh no, we won't because it's double. So -2 minus 10 is -12, and -1 plus 7 is -6. Yeah, we got a 2 to 1 situation there. Positive 6, right? That gives us what, -72? And I did that so fast, I want to make sure that I'm not wrong. So -1 to 5, the quadratic change of 6 units is 36. -72 to 0 is up 72. That's a 2 to 1 A term, and that's what we have, 2 to 1 A term. All right, so that's not wrong. All right, somebody called. I got to go make a call. End of the video. But now that's 22 through 32, I believe. Okay, ta-ta.